Okay, question 4 is about using echo sounding to detect fish in the sea. And sound waves are emitted from a fishing boat, and some of them are reflected by the fish and detected by a boat. The shortest time between sound waves being emitted and detected is 0.26 seconds. That means it's 0.26 seconds from the wave leaving the boat, hitting the fish and getting back again. And they give you the speed of sound in water as 1.5 kilometers per second. Calculate the distance between the boat and the nearest fish. Well, we're going to be using distance equals speed times time. Okay. Now our speed is 1.5 kilometers per second, but we need to put it in meters per second. So 1.5 kilometers per second is 1,500 meters per second. We're going to times that by 0.26 seconds. Okay, and what we get is 390 meters. But that's not the answer they want. Okay, this is the total distance travelled by the sound waves. Okay, but we don't want that. We want the distance between the boat and the nearest fish. Now, the boat sitting above the sea, the fish are down here. Okay, when the sound waves leave, it hits them and comes back. That takes 0.26 seconds. Now, the distance that we will have calculated will be twice the distance of the fish. So we've got to take 390, divide it by 2, so that we've just got one-way distance here. It's 195 meters. Now each sound wave is emitted for a very short time. Okay, so each sound wave, it might be a fraction of a second that the sound lasts. The reflected sound wave received at the boat lasts for a longer time. And they're not saying anything about how long it takes for the waves to get back. They're saying that once the sound waves do come back, then the sound, the reflected sound that you receive back goes on for a longer time interval than the original sound. Okay, and I know a lot of people misinterpreted this question. It's not asking why it takes a long time for the sounds to get back. It's saying why does the sound wave last a longer time when it returns than when it's sent out. Okay. Now the best way to explain this is we've got our boat at the top here and we've got our shoal of fish down here. Okay, lots of them. Now when the sound waves hit them, they reflect back. Okay, but the different sound waves are going to be reflecting back off different parts at different depths. Okay, now so we're going to get reflections at different depths. Oh, sorry. And because the sound waves are reflecting at different depths, then they're travelling different distances. Now because different sound waves are travelling different distances, they're all going to arrive back at the boat at different times. So rather than the short pulse of sound waves that we send out, we're going to get a quieter, longer pulses of sound waves coming back, all reflections from different depths within it. So rather than the short one, we get multiple sound wave reflections which last for a longer time. Now question 5 is about a skydiver, and they're asking us for an equation that links weight, mass and acceleration due to gravity, g, and we're looking for this, or any of the equations which could come from this triangle. Now calculate the weight of the skydiver and state the units. Well, weight is mass times g, so it's going to be 70 times 10. It's going to give us 700 newtons. So 1 mark for the answer and 1 mark for the unit. Should be a capital N for newtons because it's a name. Right, next part. The graph shows the vertical velocity of the skydiver during the first 40 seconds of fall. His parachute is not open during this time. And then says explain the shape of the graph. Now this word is key here. Explain. A lot of you have interpreted it as if it's asking you to describe the shape. Now a description would be saying something like it starts off steep with a high gradient, and then as time goes by the velocity increases at a lower rate until it no longer increases and it's a horizontal line. And that's a description, it's not an explanation. Explain means that you need to give the physical reasons for why this happens. Okay, so you need to go into the science here and explain why the graph is that shape. To begin with, we've got the highest rate of acceleration, and we're going to say that this is when we have the greatest resultant downward force. Okay, and this downward force is going to be the weight. Okay, there isn't going to be any air resistance at this point. Now, as the skydiver falls faster, we're going to say that there's an increase in air resistance. Okay, it starts at 0, it gets bigger and bigger. Okay, now because of this, this decreases the acceleration. It is still accelerating though, okay? It's still getting faster all the way through until we get to the horizontal part. So for the first 25 seconds, it is continuously getting faster. There's no point where it starts to slow down. Okay? Now, the acceleration is decreasing until after 25 seconds, the weight is now going to be balanced by the air resistance. Okay? And at that point, we have zero resultant force. And if we've got zero resultant force, well, it's going to go at a constant speed. Sorry about my writing there. Which is what we call terminal velocity. So my writing is ineligible there, but hopefully you get the idea. So anything from that list is going to get you on. Now for part C, you've got to label the forces on this diagram. Now first thing is, it's at constant velocity. So we should be showing the upwards and the downwards force is approximately the same size. So if you've done that, I'm going to give you 1 mark. Okay, the arrows should be roughly the same. And the downward force is the weight. Okay, weight is definitely a much better description than gravity. And up, that's going to be air resistance or drag. Now you're going to get 1 mark for each of these points. So there's 3 marks in total for that one. Now the skydiver then opens their parachute after 40 seconds. So they were going at terminal velocity at constant speed here. After 40 seconds they open their parachute. Now the first thing that we want to say here is worth 2 marks, and the first mark is showing that the velocity decreases. Now the shape of the graph should look like this, where it decreases most steeply at first, and eventually it will come to a new terminal velocity, a new horizontal line which indicates a constant speed. Okay, now it doesn't matter where you put that. You could put it like this, you could do it like this, any of these are fine. Okay, so 1 mark for showing the slowing down and 1 mark for reaching a new terminal velocity later. Okay, question 6. A student is investigating how the extension of a spring varies when he hangs different loads on it. Okay, and you've got to write a plan for the investigations, and there's 5 marks here. Okay, now you should include details of how you can make accurate measurements. Okay, so you're not just saying how it's done, you're going to explain how we're going to make it accurate. Now I'm going to go straight to the mark scheme here. Okay, the basic plan they're giving 3 marks for. Now that basic plan should be that you're adding masses, okay, that you're measuring the length of the spring, and that then you're finding extension from that. So you're going to subtract the original length of the spring from the final length once the masses have been added. So you can get 3 marks for just that basic plan. Okay. They also give you a mark if you were to draw a graph with suitably named axes, even though you also get marks for this later on. And then there's also 5 possible marks for how you can make it accurate. So they could say things like measuring it from the same part of the spring each time. So you're always measuring from the same position on the spring when you take your length. Making sure that the spring is stationary before you take any readings from it, so that it's not oscillating up and down. Repeating readings, but taking off the masses rather than just saying repeating readings, like taking a reading twice while the mass is still sitting there. It's unlikely you're going to get any difference then. So repeat readings by taking off masses. Actually check the value of the masses with an electronic balance, and then also checking that the ruler is vertical, so that essentially it's lined up right next to the spring. So it's parallel to the spring, and then we don't get what we call a parallax error, which is when we get a slightly different reading because we're viewing the ruler at an angle. Okay, next bit. Student finds that the spring obeys Hooke's law. Now you've got to draw a graph on the axis to show the Hooke's law relationship. So we're not just showing the graph for a spring here, we're showing the Hooke's law part of that graph. So we're changing the force, and we're measuring extension. Okay, we're not accepting length on this axis. Okay, and we're not accepting mass on this axis. I will accept weight, but not mass. Okay, and for Hooke's law, we're looking at a straight line. Sorry, my graph's not particularly straight. You get 1 mark for label of the axes, 1 mark for your straight line, and 1 mark for the fact that it should go through 0, 0. If there's no force, then there should be no extension as well. What I don't want to see is anything like this at the end where you're saying that as you add more force you get more extension. Okay, that is not part of a Hooke's law relationship. Okay, Hooke's law is up to the elastic limit. It then asks you to explain what's meant by elastic behaviour. Now, elastic behaviour is when an object or material returns to its original length or shape after the force has been removed, or the load has been removed. Okay. Now, with an elastic band, if you were to apply a large force to elastic band, it would be permanently deformed. So, although we call them elastic bands, they're not elastic. They show plastic behaviour, where essentially they're Now, question 7 is about a solar-powered battery charger, and we're charging it up. First thing they want is an equation linking charge, current and time. Well, charge is Q, so charge is equal to current I times time. If you're going to use the symbols, then tell me what they mean. So Q is charge, I is current, and T is time. Now we've then got to use this equation to calculate the amount of charge needed to recharge the battery fully. Okay, it says it takes 3.5 hours to charge it with an average current of 400 milliamps. Now the first thing we need to look at is units here. Milliamps, it needs to be in amps. Hours, it needs to be in seconds. So we're going to use this equation, but we're going to need to change the numbers that we put in. So the current is 400 milliamps. To get from milliamps into amps, we divide by 1,000. Just like millimeters, there's 1,000 millimeters in a meter, there's 1,000 milliamps in an amp. And then we're going to times it by 3.5 hours. We've got to turn that into seconds, so we times it by 60 for minutes and 60 into seconds. Okay, and there's one mark really for doing those workings. Now the answer you should get out is 5040, and the units are coulombs. Get a mark for each of those. Now, if the charger is moved to the shade, the power output decreases. The voltage across the charger stays the same. Explain how moving the charger into the shade affects the time needed to recharge the battery fully. Now, lots of you have kind of assumed that this is something to do with an LDR, light dependent resistor. Now, there's no evidence in the question that it's got anything to do with that. So, any comments on such as the resistance of the LDR changes as the light intensity on it changes won't get you any marks here, because this has actually got nothing to do with an LDR. Okay, it's a solar cell that works in a different way. So what we're looking for here is the fact that if it's in the shade, there's less energy input. Okay, and we're going to be dealing with energy later on this year then, but essentially it should be reasonably obvious that if there's less sunlight, it's going to be getting less energy, and that's going to cause a decrease in current. Okay, because the more light energy you get, the more electrical energy you get out. And if we wanted, we could kind of look at this in the equation here, that the power output in the solar charger is going to be equal to current times the voltage. The voltage, they've said, stays the same. If the current goes down, then we'll have less power output too, so it will take a lot longer to charge it up. Now, question 8 was only for the students that were doing the specialist course, so if you're doing the standard, you don't need to worry about, well, you still do need to know most of the stuff on this, but obviously it wasn't on your test. Now it says, a student wants to find the refractive index of a glass block. Draw a diagram to show how the student could set up the apparatus. Well, everything should be labelled here, so you can have a glass block, you can have a ray box, and a light ray is going to be given off by that. Okay. Whenever we draw any diagrams like this, we should draw a normal line on. Okay, and we're going to show that the light refracts as it goes in. Sorry about my pretty dreadful diagram here. And that. So everything needs to be labelled here. So I want the ray box labelled. I want the glass block labelled. But also, how are we going to take measurements of this? Well, we need to be measuring the refractive index. So we're going to have a protractor in here, which should be labelled too. Now, what measurements should the student take to find the refractive index of the glass block? Well, you need to have the angles of, two angles we need. We need the angle of incidence, can't spell, and we need the angle of refraction.